areas that go to the active structure. And as you can see, the protein undergoes a very dramatic and complex change in structure. The time scale for exchanges are nanoseconds, tenths of nanoseconds. And just to have an idea of which parts of the protein are moving, this thermal map provides us colors where the ones in red are the ones that have the highest exchange in deuterium protein, and consequently are the ones that have the higher changes in exposure. Consequently, you can see that just wherever you are, that there are specific regions of the protein that undergo these changes, when others remain relatively constant. So, what do we learn from this? That a relatively simple reaction that can be catalyzed by an enzyme requires for the protein to undergo a very dramatic pathway in changes in conformation, from the inactive to the active and then backwards, through apparently a similar pathway, although we don't know if it's exactly the same. Obviously, the resolution of these observations is very poor, but it provides us with the idea that the enzymatic reaction requires a very complex change in conformation and energy-consuming process by one particular enzyme. So the reaction is assured, but now the problem is transmitted to the protein. So the cell has to somehow make sure that the protein goes down. The next example, Adrian will describe.
Well, thank you for the invitation, especially to Dr. Zentella. I will talk to you about a very specific example, a very basic concept in biophysics, which has to do with the generation of action potential. So, as you may remember, the extracellular fluid and the intracellular fluid have different composition, specifically ionic composition. Sodium ion is the most abundant cation in the extracellular media, whereas potassium is mostly abundant in the inside of the cells. So, the lipid layer of the membrane is impermeable to the movement of ions, since they are charged particles, but cells sort this out by locating proteins in the membrane, such as ion channels and transporter, which allow the movement of these ions in a very controlled manner. This was studied since 80 years ago, especially in the beginnings with the axon of the giant action of the axon of the squid. And it was found that measuring the electric potential, comparing the inside of the cell compared to the reference electrode in the extracellular solution, cells have a negative electric potential. And this is important because this allows excitable cells, such as neurons, a way to communicate with each other. When a certain stimuli arrives to the cells, the membrane potential depolarizes, reaching positive potentials, which then are, and then we observe a repolarization that allows the cells to come back to the potential and fire a new action potential later. So, an interesting tool to study this phenomena was voltage clamp studies, where you can modulate the voltage and then measure the current. So in the 50s, it was found that there is a complex current in response to a depolarization. First, we see an inward current and then an outward current that finishes the moment that the stimuli finishes. And it was found that actually this current is due to two different currents, mainly due to potassium ions, the outward current, and the inward current is due to the sodium ions. These are the macroscopic events that we can measure thanks to the whole cell. But how do the proteins that I talked to you about control this macroscopic recording? Well, patch clamp studies allowed us to study this, where a micropipette is used to attach a very tiny piece of the membrane, where only a single of these protein is located, an ion channel. And then you can measure the current that is due to a single protein, so a microscopic event. Performing similar studies as the one that I showed you before, only that is single channel, we see these kind of recordings. There is this opening of the channels and sudden closing, but these are all different. A single channel does look quite different to another, and there is a certain probabilistic event of this. When you sum these events up and look at the average of these hundreds or maybe thousands of events resemble the macroscopic current that I showed you before. This is true for sodium channels, and the same is true for potassium channels. There is sudden and random openings and closings of the channel, as you can see here. But the average of all these proteins in the whole cell gives rise to a highly predictable phenomena in cells. So this is the result of the different non-conductive and conductive states of ion channels that dictate the membrane conductance and these responses in excitable cells mainly. We talk about closed states in sodium channels that are energetically favored when the cell is in basal conditions, but when a stimuli arrives, this channel open and allow the movement of ions. Now, this open channel, the energetic pathway favors the transit to an inactive state that allows the repolarization of the action potential, and so the cycle goes on. So this is a way that probabilistic transitions between different states are used in the cell by having hundreds or thousands of these proteins to make up an all or nothing response in cells. So, yes.
This, for example, analyzing the changes in structure have not been possible because this can only happen when the protein is in a membrane. And so analyzing the deuterium exchange, for example, is very difficult because the amount of noise is too high. So there are no experimental data with respect to the change of this proteins. Actually, protein membrane conformational changes are one of the great barriers that haven't been solved in structural biochemistry. I want to end with a more complex example, and what we are doing is we're going from very simple biochemical reactions to macromolecular changes, which are the proteins, and now look at how cells respond. The example that I have chosen is tumor necrosis factor, which is a soluble factor that belongs to the immune system, and it is relevant because it participates in the inflammation, which we have heard before, but it's also part of the system that serves for anti-cancer survey by the immune system. It has been postulated tumor necrosis factor serves to kill tumor cells in the young person, and it's only those that mutate and become resistant to this effect that become tumors in the later ages. Tumor necrosis factor is a soluble product. It has its receptor, and it tracks curiously with two pathways. One that will activate cell survival, defined by a particular transcription factor called nuclear factor kappa B. But it can also activate in parallel the activating of enzymes that clip proteins that belong to the family of caspase that are essential for the cell's suicide or apoptosis. It has remained a very complex question how the cells decide to go one way or the other. What we know experimentally is that, for example, tumor cells or cells that have been infected by viruses go this pathway, whereas normal cells that have none of these characteristics go this pathway, and they become activated and respond. So, for example, if this cell dies, it will liberate different factors that will activate TNF. This TNF will activate this pathway on a neighboring cell, and so the neighboring cell will say something like, "Oops, my neighbor died, so I should be prepared." Okay, so this is just, and what I want to show is just that the time scale of events now here is, we're looking at the liberation a cytoplasmic enzyme, so this is a cell membrane. We measure an enzyme that is released, and this allows us a very objective measurement of cell death. And you can see that the release starts between 10 hours after the stimulus. So what the hell is the cell thinking about? If it's going to die, why doesn't it die right away? And different cells have different lag periods to start the death process. And what we're looking here is really, again, a population event. So we have some cells that start dying very early, and then we have some cells that even after 20 hours after the stimulus are initiating the death process, but in a very delayed manner. I'm not going to provide you with any specifics because there are none. I just wanted to show you the complexity of what is now trying to be put together. We have to analyze the way the signals go from the membrane into the cell and activate this process. We have a lot of measurements, and therefore we could create models, and there are different models that have been generated. By differential equations, for example, or by causal formula or logic vectors. We have to deal with the gene regulation. I told you NF-kappa B is a transcription factor. It will change the composition of the proteins expressed by the cell by inducing the expression of some genes and turning off the expression of other genes. Here, for example, Bayesian networks, logic networks have been useful tools. And then we have the metabolism, which is something that is gaining more and more importance in understanding how cells respond. That require different, not that require, but have found specific models to best explain their behavior. Now, where we are now, if we try to explain a cell behavior, is we have to somehow put all these together. And this is a big problem. Unless we solve this, we will not be able to explain the tissue behaviors, from which we have a lot of information. This is a very interesting paper of a group of mathematicians and engineers that created a network system trying to generate a prediction as to how the cell decides to go cell death, which is in this side, here is CNS, or if it decides to survive, in other words, if it goes left or right. So some of these processes have started to be modeled, but this is where we are right now. We don't have enough experimental models to provide results in the back so that can support if this particular model is effective. I want to end with this view. What we have tried to do is to explain that, for example, a particular molecule, in this case tyrosine with ATP, can go different reactions, the phosphorylation of the alpha, the beta, or the gamma phosphate. It just so happens that under living conditions, it will always go to the gamma phosphate. So this is what living systems do. They favor a particular outcome. Now, if all this happens at the molecular level, there is a threshold. Once this threshold of molecular events has been reached, it starts a different level, which is a macromolecular. In this case, would be something like the channels that are being affected. The channels open, but they open in a very specific manner. And this generates a macroscopic event. In this macroscopic event, when it reaches a threshold, it will activate cellular events. And cells themselves will behave in a very similar way. They will go a very specific pathway depending on the signal and if the threshold has been passed. So interestingly, I would like to propose to you that the way if we were to construct this, it looks like a fractal structure, because every time you reach a threshold, a new ramification occurs. Now, in this case, this ramification is a ramification at a different scale. And finally, what I find a very interesting hypothesis is that for biological systems to favor, in all these cases, a particular case, whether it is a molecule, the protein, or the cell in its equilibrium, it has to be in what is charted here. This is for proteins. If you look at the conformation of proteins and you look at all the population, in this case, they have been divided in three orders, which are rigid structures, partially ordered, and malleable structures. Living systems require malleable structures because the reactions need for the protein to capture one thing, move it to close, approach the other reactant, generate the result, and display it. So this cannot be done in a rigid structure. And this particular malleable structures represent systems that are far from equilibrium. To remain there, they require huge amounts of energy. And this is where we're now. And I just end with a list of tools that we are trying to use. Unfortunately, the tools, as you have seen, are applied to different levels in different manner. The big problem now is how do we sum all these levels to provide the explanation of how a cell moves, a cell behaves. So I just want to end my presentation and probably this meeting by thanking Tim for his friendship and most certainly for challenging our influence. Thank you very much.
Questions? Is an analysis of apoptosis an individual cell effect, or is there such a thing as a collective effect?
The modeling that I presented is presented for a single cell process. Now, they have, in this paper, they have what they could not solve is how do you explain that this lag in the population process. This is what they are proposing is that this model can serve the moment the cell initiates the process of cell death. But apparently there is, from the signaling, the initial signal, to the initiation of cell death, the cell appears to be thinking about it. Or the system is fighting with itself. And this fighting itself, I think, is a very interesting area because it implies what to us as humans seems a very obvious thing, which is taking decisions. Now, cells take decisions, very important decisions, but they don't think about it. They base their decisions on equilibriums.
What about time scales? Can some of these things miss the signal because of metabolism alterations?
Well, the time scales are very different. For example, I mean, the enzymatic, the structure changes in the enzymes are in the area of tens of nanoseconds. Changes in current, just the whole the microscopic currents by milliseconds, tens or hundreds of milliseconds. And the cellular responses require hours. So I think that these differences in time scales imply that as we go higher in the order of complexity, the requirement for finding themselves in this semi-equilibrium is more difficult. That's what my impression is. It could be any other thing. I don't know if it serves your question.
Well, let's thank the speakers.